Good afternoon. So let's get started. So welcome to the weekly CERIAS security seminar. Today it's my great pleasure to introduce Professor Adam Bates from the University of Illinois at Urbana-Champaign. Adam is an assistant professor in the computer science department at UIUC. He received his PhD from the University of Florida, where he was advised by Professor Kevin Butler in the study of computer systems and cybersecurity. Adam has conducted research on a variety of security topics, including SSL TLS, cloud computing, USB attack vectors, financial services, and telephony infrastructure. He's best known for his work in the area of data provenance, particularly the construction of secure provenance-aware systems. Adam?
Great, thank you. Thanks so much, Jung Young. It's a real pleasure to be here today. I think that the work that comes out of the CERIAS lab is work that I probably pay attention to just about as much, if not more than anywhere else in the country. So it's great to be here to tell you about some of the things that I've been working on. So today I'm going to be talking to you about some of my recent work in the area of secure data provenance. And so most of you in the room are probably wondering, what is data provenance? And hopefully I can convince you that it's quite important. So in 2012, there was this Massachusetts drug testing laboratory. They did a lot of work for court-ordered drug tests. And they found that two of their lab technicians they'd been arrested for tampering with these court-ordered drug tests. So in the aftermath, the lab couldn't even say with certainty which of these test results had been tampered with by these corrupt technicians, which called into question the authenticity of all of their results, and with it, over 40,000 drug-related convictions. So in this situation, it was actually a lack of data provenance that led to this disastrous result. Data provenance is metadata that's generated by a computer system that describes the history of the processing tasks it's performed. So we can look at an object's data provenance to determine how that data object came to exist in its present state, which allows us to reason about its value or its integrity. So in this case, the provenance could have been used to identify those drug tests that had been tampered with, or perhaps even more importantly, those tests that hadn't been tampered with. So we're probably not going to be able to see this very easily from where you're standing right here, but here's an example of how we might model one of these the provenance of these objects in the form of a relation graph. So what we can see here is that we're starting with two samples, lab sample A and lab sample B. In this next column, we can see that they were both subjected to legitimate data processing results by one of our trustworthy technicians to produce a clean result A and a clean result B. At this point, though, one of the corrupt technicians actually opened up the second result with a text editor in order to generate one of these forged results. So if we'd had this data provenance in the case of the drug testing facility, we would have been able to say, convictions based on results A are still legitimate, whereas those with results B, they need to be brought back into court. Slightly more recent result, or slightly more recent motivation example. Why on earth did the DNC allow 20,000 of their sensitive emails to leave their corporate network and fly out into the ether to some unknown domain in a foreign country, right? Well, the answer to this is complex and kind of spans multiple layers of computer security challenges, but one of them is that our network security functions today, they don't really have the context necessary in order to examine a network packet and make a highly contextual decision like, where did this packet come from? What data is inside of this packet? So provenance can provide this type of context, and it's going to play a crucial role in future security mechanisms. Data provenance is effectively of use in virtually any scenario where a context-sensitive decision needs to be made about a piece of data. We might imagine that, or actually, in fact, provenance is a strategic priority for the Department of Homeland Security and various health industries, for DARPA, and for national laboratories. But just having this information isn't enough, right? We also need to be able to secure it. If these lab technicians that were already untrustworthy or these hackers are able to break into these machines, it would surely follow that they would also attempt to hide their tracks by tampering with these records, right? So it's important that we have a way of establishing trust in the correctness of this data provenance that we're collecting. We also need to make sure that these provenance-aware mechanisms are performant, right? That they're imposing a minimal overhead on our systems by only collecting the context we need while minimizing the capture of unnecessary information. And so today I want to talk to you about two of the systems that I've recently developed that address some key challenges, specifically in the area of efficient and accurate capture of this data provenance. First, I'm going to be talking to you about a mechanism that we introduced to dramatically reduce the storage costs of collecting this fine-grained audit data through the introduction of a policy-based compression mechanism. And then subsequently, I'm going to show you, even if we're collecting this information at a certain layer, like at the operating system, there's important things that are happening at other layers of our architecture that we also need context about. And so we actually need a way to fuse provenance that's being captured from different sources. And so I'll show you how we took the example of a very complex web service and introduced provenance functions without requiring any modification to the web service itself. So before we delve into all that, a bit more background on what data provenance is. As I mentioned, it's metadata that describes the history of an object as it's being processed on the computing system. This history details what's happened to the object from the time it was created, including how it came to exist in its present state. So as I showed you before, we can model provenance as a relationship graph, and we have a highly simplistic one here. There's three principal objects in our graphs. These vertices are entities, which sort of represent various kinds of data objects like files or sockets, activities or processes, and then also agents. So what we see here in this graph is that this is the provenance of a file called output. It was generated by some process which read into input files, and by the way, it was controlled by a particular user. So as I mentioned, having this information is one thing, but the ability to secure it is highly important. Given its value, it naturally follows that data provenance is a ripe candidate for attack. And so one sort of defining characteristics of my work in this space is that I think about collecting this information in the context of an attacker that's gained access to our system, is aware that this, this incriminating information is being collected about their activity, and is therefore trying to mess with that, right? They could attempt to disable the mechanism that's recording this data provenance, avoid taking certain actions on the system in order to remain invisible to this mechanism, or they could even attempt to inject uncertainty into our records in some way, shape, or form. So I'm not going to talk about it at length today because I'd like to talk about some newer stuff. But in prior work, I introduced a provenance collection mechanism that can reliably collect this data provenance in the presence of such an attacker, called Linux provenance modules. And for our purposes today, all we need to understand is that this is an extension to the Linux operating system that establishes a provenance layer within the system, so that anytime either something in user space or something in kernel space attempts to perform any task that manipulates a principal kernel object, virtually anything we can think of, like files, packets, processes, disk partitions, so on and so forth, we're able to record a record of it. And so effectively what this provenance layer does is that it just pumps out a stream of information from the kernel, which we can think of as like an ultra fine-grained audit log. And then this architecture in user space, it processes it into these really nice relationship graphs that succinctly describe what it is that's happening in the system. We created this system. We proved that it had certain security properties that prevent it from being tampered with by that attacker. I have backup slides if you want to ask me more questions about that, that's fine. But we evaluated it, and we found that we could actually collect this information really quickly, like without messing with the system's performance at all. In fact, under realistic workloads, we could collect this provenance information with just 3% overhead, right? So, almost negligible, not quite. Then we could also, perform certain tricks to query this information really quickly, on the order of milliseconds. So even if I had, these massive files of days and days worth of system activity, I could actually represent that in such a way that I could very quickly say, well, what's the provenance of this particular file, and that would output that information. So that would mean that as an administrator, I'd be able to quickly figure out what's going on in my system. There was one problem, though, and that's something that the CERIAS lab has spent a lot of time thinking about, and it's also one of the core challenges of what I'm going to be trying to answer today. If we looked at the storage overhead of what this system introduces, it's quite awful, right? So this is a 10-minute capture using this LPM system, using a couple of different backends. So let's see, we were compiling a kernel and then recording the provenance of that kernel as it was being created. So in the worst case, if we just took that entire stream of information here and put it in a data file, that generated 4.5 gigabytes of log information in the course of 10 minutes. Now even with our naive solutions to the storage problem, it wasn't quite that bad. So we were able to, we could store it in a zip file, and all that redundancy goes away. I bragged about the speed with which we could query. That's on the order of maybe 20% storage cost. But this is obviously still a huge problem if we want to start thinking about recording this information for days, weeks, months. Yeah.
Does your 3% overhead numbers?
Oh.
Press the button. He has it.
Oh, this is fancy.
Does the 3% overhead cost that you quoted include the cost of compressing your data stream?
Yeah.
Yeah. Okay.
Yeah. So that ends up not being a bottleneck.
Okay.
The actual cost of interposing, what we're actually doing is we've got a hook architecture under the hood here that's interposing on all these different call paths in the kernel to pop the context, read what's going on, and then sort of pipe this out via a relatively efficient Linux kernel relay. Yeah, so that includes the storage cost. But if we, let's see, I think I've got it jotted down. If we imagine that this was the amount that we'd need to store over the course of 10 minutes, then let's see, that's 650 gigabytes in a day. That's 4.5 terabytes in a week. So this raw cost of storage threatens to seriously undermine the usefulness of this information. Data provenance is difficult to store, and it's difficult to process quickly once it grows up. So we could improve that a bit by using a number of different tactics that have been proposed coming out of Purdue. We could find ways to further compress the log. We could filter events that don't contain any useful information, like maybe like temporary files would be an example of something that no one really cares what happened with that temporary file if it was created by one process and no one else ever read it. So we could cut those things out. But even in the presence of those techniques, we're still going to be logging gigabytes of provenance a day over time. So here's what I find to be the most frustrating thing about that. Let's take a look at what is it that's in these massive provenance logs. In particular, with the Linux provenance modules, we're collecting provenance over every single thing that happens in the system from boot time onwards. And so we actually have this massive relationship graph that stems from a single node in the system. But if we imagine that we're an administrator that's trying to deploy a server or a container or whatever else for a particular purpose, let's say it's a web server, odds are we're only ever really going to be interested about the things that actually pertain to the intended use of the machine, right? Meanwhile, we've got cron jobs running in the background and other sorts of system noise, the startup process, all the things init did that don't actually inform our Apache web server. We really only care about our web server, maybe a helper application like htaccess that provides auth for Apache, maybe a database backend, things like that. So optimally, we'd be able to store just the information that we care about, but throw out all of the other information that we need. But we run into a problem here, and this has to do with one of those security properties I glossed over when I talked about LPM, and that's the matter of completeness. When we collect this information, we want to make sure that we have a authoritative record of everything that ever happened with regards to a particular system object. So if we say, well, I only care about the things that Apache does, what happens if Apache does something we don't expect, right? it's a long-running program. Eventually, it decides to read in an object from somewhere else in the system, right? Maybe this is actually an unauthorized file access, some bug in Apache, and so it's read a file that we didn't expect it to. Unless we were recording the provenance of this particular node the entire time, then we'd be in real trouble here because we no longer have an authoritative, forensically valid description of what it was that Apache was doing on the system. So it ends up being quite difficult to sort of prune out what we think of as uninteresting information because we can't make a definitive statement about what might eventually be interesting later on in the system. So if we're going to start selectively recording this information in order to save space, we need to have some idea about the future events that are going to happen in order to maintain some assurance of completeness. So the first fundamental challenge I want to talk to you about today is just that. Is there a way that we can collect a complete description of one application's activity while safely ignoring that of other system activities? So it turns out there is. We propose that mandatory access control provides exactly an environment in which this challenge can be overcome. In a Mac-enabled system, every object is assigned a security label, and there's a policy that dictates the permissible interactions between those different system objects. So if we can figure out a set of system labels that can appear within an application's provenance history, and only collect provenance for objects that are assigned that label, we should be able to safely filter out the provenance of any other things that are happening in the system. So this figure on the screen here provides an intuition of what it is that we're proposing here. As I showed you down here, we've got another sample provenance graph that shows some relationships between different objects in the system. But we can also take a security policy and model it as an information flow graph. So whereas provenance is a history of what happens in a system, an information flow graph can be thought of as like a future of permissible actions on the system. And we can actually overlay the information flow graph onto the history of events in order to make informed decisions about what it is that we need to collect on the system. So, in other words, we're going to analyze the relationships that exist within the information flow plane in order to filter out the activity of what are effectively unreachable objects in the provenance plane. So using the Linux provenance modules framework, unsurprisingly, it's modular, right? We implemented a mechanism that enables this functionality that we call provenance walls. Yeah.
A quick question. Mm-hmm. So for the provenance wall, do you actually assume? Yes. Here we go. Do you assume that the system has not been compromised? Because if I understand correctly, if the system has been compromised, then some of the MAC policy enforcement may not be working properly, and then you start to see kind of information flow going rampant or going out of their regular pattern.
Right.
But that's exactly the moment when we need provenance.
Of course, yeah. So the question was, effectively, are we trusting the kernel?
Exactly.
And if so, why is that reasonable?
Exactly. Or any, yeah.
Right.
Any of the processes that are running
right.
that might have been compromised.
So I would argue that probably one of the primary reasons for enabling mandatory access control is to assure kernel integrity. Exactly. Right. Yeah. So by no means,
so
right?
It's a chicken and egg kind of a situation.
Yeah, I guess so. So the issue of providing a 100% correct security policy is somewhat orthogonal to the work. Yeah. But what does mandatory access control buy us normally? Yeah. Well, it hopefully buys us kernel integrity. Right, certainly like a full-featured Linux security module like SE Linux, has a default policy that is somewhat permissive in user space, but is supposed to harden anything related to interactions with kernel subjects and kernel objects. Okay. And then additionally in SE Linux, applications can define their own policies to permit what's supposed to be happening on the system, creating these subdomains of system activity. So there's sort of two concerns that Mac is trying to solve for us, both of which are least privilege in the end. So we certainly want to make sure that our kernel isn't compromised, and if it is indeed game over if that's the case. But another thing that we want our mandatory access control to enable is least privilege in user space. If Apache is compromised, It should only be able to do things that Apache is supposed to do. It shouldn't be able to interact with the rest of the system. Now, if something really important like Apache is compromised, there's all sorts of bad things that can happen within the confined space that Apache is permitted. So we still care about the provenance of that mechanism. But so I guess that's a long answer to your question. In short, yeah, we're assuming that the kernel's correct at the time of installation. We do want to account for attacks on kernel integrity, but our leveraging on past work is effectively how we do that. Right. So here's another look at what LPM kind of looks like under the hood. We have effectively a second reference monitor on the system where things are happening in user space. If the security mechanisms in the kernel allow it, then we're going to record provenance for that operation before it occurs and store it. So what provenance walls does, it sort of adds, what I'm going to slightly inappropriately call a training phase because there's no machine learning here. But so we have a policy generator for data provenance that takes as input the security policy of the system. Oops, sorry, screen. And then also a minimal amount of administrator preference, something like, what application is it that I care about on this system? So given the security policy and the administrator's preferences, we generate a provenance policy that's loaded into the kernel. And at that point, whenever a new event occurs, the provenance monitor is going to pop the security contexts of the objects involved in that event, decide whether or not they match the provenance policy, and if and only if that is the case, will we generate a new event. Otherwise, the provenance monitor takes no action. All right, so that's the goal of the system. Now we need to figure out how do we actually do this? What is formally the goal that we're trying to provide when we say I want to collect everything I need and nothing that I don't? So for that, we're going to need to introduce a little bit of notation and define a couple of formal properties. So let's see, what do we got here? Let's say E is the set of all event tuples that happen in the system. G is a provenance graph that describes the execution of E. Now, I is a subset of E, and those are the things that the administrator actually cares about. So we might imagine, all of the event tuples that inform Apache. And then finally, we have a provenance function P, which is effectively a query. It returns all of the events in G that pertain to the history of a particular object. So before, our goal was completeness. For every object X that we can find in our set of event tuples, we need to return all of the other events that pertain to that particular object. We can begin to relax that by saying, okay, if you're an object X that appears in the set of events that I actually care about, then we need to return everything, undefined behavior if you're not in the set I. And then what we're striving for with provenance walls, if you are in the set of interesting things, return everything. If you are not in the set of interesting things, then return nothing. All right, so given that definition, we now need a means of partitioning the set of MAC labels so that for a particular target application S, the policy satisfies this property of minimal completeness. So as I pointed to, our solution involves analyzing the system security policy in order to identify a set of security labels that constitute target application's trusted computing base, or TCB. So the TCB can be thought of as the set of objects upon which a given application depends. And intuitively, if we collect provenance for every single object that's within an application's trusted computing base, we should have a complete description of that particular application's history. All right, so here's our solution for that. We need to, this is our solution for calculating this trusted computing base. First, we have a security policy and all of the associated mandatory access control labels, which we'll call L. We have a target subject S. So first, we identify all of the subjects on the system that can write to the kernel. Again, if you can write to my operating system, I necessarily need to trust you. So all of our kernel writers are included in our list of trusted subjects. We also have all of the subjects in the system that can write to my target application's executable. Again, if you can overwrite my application binary, then I necessarily need to include you in my trusted computing base. And then finally, we have T sub h, which is the set of subjects that can write to my helper applications. So you'll recall I used in my example Apache. Apache actually identifies additional applications and subjects within its policy, such as htaccess, which says, this is a different entity, but I depend on it. And so we need to identify all of the subjects that can write to those helper applications.
What is the granularity of subjects? Are they processes or threads? Or it could be something even smaller?
So what is the granularity of subjects? So they are mapped to processes, right?
Okay.
Or can they be mapped to individual threads? I'm not sure.
Okay.
I'd have to go look at the process control block and remember. So yeah, but we're in the order of processes and threads. Basically, a user will be associated with a particular security context, and when that user invokes something, the subject label is passed on to the application. So it's not a one-to-one mapping. A process could run with different security labels at different times, obviously. So these three groups of writers combined form our set of trusted subjects. So to identify all the objects on the system that we trust, we take the set of untrusted subjects on the system, and we say, if none of the untrusted subjects can write to you, then you're a trusted object. And so that gives us a trusted computing base, which is the union of all the trusted subjects in the system and all the trusted objects in the system. And despite this complexity, I did mention a human earlier. This is actually the only thing that we need from the administrator. If you can tell us the application that you care about, aka the subject that you care about, then we can identify procedurally the entire trusted computing base of that particular application by mining the policy. We took this system and we deployed it against a variety of applications in order to figure out what was going on. We first considered three different sort of forensic investigation scenarios where an attack has occurred and an investigator wishes to attribute that attack to a certain agent in the system. So for each of these cases, a web server, an FTP server, and a database management server, we went on to exploitdb.com and found a working exploit for that attack, as well as the SE Linux security policy associated with each of these applications. And then we turned that exploit into a workload by interspersing it with hundreds to thousands of legitimate requests. We also considered a fundamentally different scenario, which we thought might be pretty cool, relating to that of managing and monitoring a cloud computing infrastructure. So here an administrator might wish to sort of monitor the configuration of their host machines without capturing all of the activity that was being generated by the guests in the system running within VMs. Since VMs are isolated from the host through virtualization, we were able to take the KMU KVM policy and minimally modify it in order to create a provenance policy that represents the scenario. And then within the VM, we ran a postmark benchmark in order to identify what was going on. All right, so here are our results. And so what we're effectively seeing in each of these domains is it's kind of a mixed bag. In all of the forensic scenarios, the amount with which we were able to reduce the size of these logs varied from 32% to almost 60%. In the case of the cloud provider, though, we were able to reduce the size of the provenance log by 90%. Effectively, what this says is that first of all, we have a highly sort of domain-specific mechanism for savings. Your use case is going to depend on whether or not this is going to be a good tool for you to use. In the cases of the forensics investigations, the web server, the FTP server, and the SQL server, that was what we cared about. So it's not surprising that we weren't able to get dramatic reduction because we said, pay attention to these things. And so, the background noise in the system was the only thing we were able to filter out. And in some cases, that was only a minority of what was taking place. In the case of the cloud provider, we actually identified a scenario in which the thing we cared about was actually generating a minimal footprint on the system. And so we were able to see a lot of savings as a result of deploying this policy reduction technique. So I'll mention it again here before you have to leave. The cool thing about this is that this can be easily composed with any of the other methods for reducing provenance costs that we've seen. We're not leveraging any knowledge about common data processing paradigms like something like loggc would. We're not leveraging information about the internal semantics of a program like execution partitioning does, right? The good news is, while this isn't the total solution to our problems, it plays very nicely with some of the other things that are appearing in the literature now. Cool. So now I'm going to pivot and talk about the second piece of work. If you'd like to step out now, I see it's about 5 o'clock. That's okay. Okay, great, good. I've talked about using web applications as a motivating scenario throughout this talk thus far, but there's actually another pretty significant problem if we're trying to capture the provenance of a web server. So what we have here is kind of a dummy workflow for a web application. We've got lots of clients connecting. The web server has some number of worker threads that are happening. We've got JWorkers here. But then this is, a stateful web service, so it's actually performing a lot of communication to a database backend as well. Let's think about what the provenance of an individual web request might look like. I'm client I. I send a request to, Facebook.com or what have you. Facebook processes the requests, queries some data store, and sends me back some results. So we might expect that our provenance would look something like this, right? The web application received my response. It used some information that was provided by the database, and then, it received my response. It used some information that was provided by the database, and then it sent me back a web response, right? So there's a problem here, and it has to do with a semantic gap that exists between the operating system and user space. This is actually what the provenance would look like. Because we have a whole lot of different clients connecting to this particular web server, client I, if we don't understand what's happening under the hood in this web service, we end up in a scenario where we have to conservatively assume that this response, the response to client I, is actually dependent on all of the other work that the web server did previously. So this general problem is delightfully called a dependency explosion, right? So we've got all of these different relationships that exist in the provenance of this particular web app. It's not actually true. This is a false dependency, and also it makes these results almost completely unusable. And so that was a toy scenario, right? This problem only gets worse as our applications get more and more complex. So, what we have here is a AWS-based or an EC2-based web app service. And we can see, or perhaps we can't see that, within this figure, we have load balancers and application servers. We have a number of different database backends, and we also have a test environment that the users of the developers of the service are using. And so, as we think about this dependency explosion problem, if we took this workflow and sent it through a realistic work application, we would just have a completely unusable record of that individual web request that would basically span the history of everything that's happened in the system. So this semantic gap problem is real. It leads to false provenance, and it very much threatens to undermine the usefulness of these things that we're doing within the operating system. So there's a lot of different solutions to this problem, and some of them have been proposed by Dongyang and the group here at CERIAS. We could instrument the application to make it provenance aware, would be one straightforward thing to do, right? So for example, in the case of Apache, we could ask Apache to let us know every single time it's starting to field a new request. And that would allow us to decompose those individual web requests into autonomous units of work, right? So that's something that's come out of here, using program analysis and transformation, and it's really great. But especially when we think about this environment, we don't have the source code for all of these different web components, right? This is all owned by different developers. They might not be particularly interested in helping us get this fine-grained audit information that we want to. It might violate some license somewhere for us to instrument the code in a certain way. So while those approaches are promising, we wanted to adopt a slightly different usage model where we assumed that we didn't have any developer cooperation, we didn't have access to source code, and we didn't want to instrument any applications. So we basically wanted our web service to work exactly as it used to without us having to intercede on anything in practice. So this leads us to our second challenge of the day that I want to tackle with you. Is it possible to observe these application-specific workflows without actually needing to modify the application? So thinking back to this sort of cloud-based scenario, we thought people layer on security solutions to networks all the time, right? You know, that's what our firewalls are and our IDS, and all these different sort of security-oriented middle boxes. Can we take this similar concept of network function virtualization and then apply that to the auditing problem as well in order to piece together this? And so that's exactly what we did. We proposed that let's introduce some network provenance functions to go alongside our security functions. And what these NPFs do, you know, the core insight is that an operating system under the hood, you know, it can't easily make sense of the internal state of an application, but it is relatively easy to interpose on communications between different components in a system through, you know, different kinds of IPC or network proxies. And since so many of these protocols that are being used to communicate between components is moving in the direction of standardization, you know, we've got all these ubiquitous protocols like HTTP and SQL and different types of message passing protocols. It'd actually be pretty straightforward to parse those in order to extract the ways in which different components are communicating with each other. And so if we're able to understand what the communications are, we can then generate provenance that describes the interactions between components. So in order to enable this, we're going to introduce this box here. Orange is the things that we've messed with. So we have our LPM provenance modules in the operating system, but between components, so that we don't have to manipulate the actual application or the actual database, we're going to implement an explicit forward proxy that basically interposes on the traffic, it parses the communication, and then it generates provenance. And we can spread these proxies all over our web service and have all of that information aggregated into an individual provenance data store. So what we did was we performed a little bit of minimal modification to the web server, but not the application, in order to facilitate execution partitioning. And then for the rest, we applied these proxies to interpose on components in order to figure out the ways that they're communicating with one another. So here's a example of how this workflow might be modified. Just like before, we have an incoming web request that reaches our web server. A single line of code inside of our web server before the application code is reached notifies our provenance record that a new unit of work has started. The application parses the request and then sends a request out to the database, which is intercepted by a database capture agent that in turn generates more provenance and sends that into our provenance store. It checks the return values of the database. And then when we reach the web server again, we notify our provenance store that this particular unit of work has ended. So now we've been able to partition the execution of the server. And moreover, we're able to provide linkability between the different application components in our system. All right, so just a couple examples of what these network provenance functions actually do. So let's take a look at, how would we parse a SQL request in order to turn it into a provenance record. So here, let's see, we have a select statement where we look at the employee ID, the first name and last name of the employee, the table where this information is coming from, and then we filter our results based on their salary. So we take the SQL query and then use a Bison grammar to turn it into a parse tree, right? And it's very easy to see that all of the different data entities exist in the leaves of this parse tree here. So our take on this is that obviously we want to have a record of the explicit data accesses that are happening, like the values that are being returned. We're going to definitely create a record that the employees ID field of the employees table was accessed, that the first and last names field of the employees table was accessed. But then also we have this filter function here. So even though we're not returning the salary, we're clearly leaking information about the contents of the salary field, right? So our solution to this was to extend the provenance grammar to refer to these as implicit data accesses. And then in the case of ephemeral constants and things like that, we don't record it at all because we assume that that doesn't really contain any meaningful information. So based on this sort of labeling, we can then create a provenance graph that says, all right, this select statement made use of these three fields. It made implicit use of this particular field. And then all of these tables were a member of, all of these fields were a member of the employees table. And so, we can take that intuition and apply it to a number of different protocols. Basically, any form of structured data we can apply these tricks to, right? In the case of some SOAP encoded remote procedure calls, again, we can sort of look at the body of the SOAP envelope in order to infer what sorts of relationships exist within this particular request. All right. So we went ahead and implemented this system. This was a bit of a more complex deployment. For the different applications, we were continuing to collect information within the operating system. So LPM is still out here. We deploy this virtualized provenance collection functions. As I mentioned, we made a small modification to the Apache web server since we didn't have Dongyung source code. Rather than use his automated tool, we just added a couple lines of code, and by a couple I mean less than 5. So that's how straightforward it was to bias the execution partitioning step. And then we have this provenance recorder that maintains an in-memory graph of the provenance of these different objects. All right. So we tested the overhead of this system against a bunch of different realistic web service workloads. We used sort of the iconic Dell DVD store benchmark, Ruby's, and Wikibench, which is what Wikimedia or WikiLeaks is based off of. And so in spite of the fact that we're performing this pretty invasive interposition on these intercomponent communications, it turns out we're still able to impose a relatively modest overhead on these different web services, just 11% end-to-end overhead on these realistic workloads. There's an argument to be made that we can use these network provenance functions in order to compose a sort of complete holistic view of what's happening in these complex systems where we don't have access to the code. So what does that exactly buy us? Well, one, as I mentioned, if we think about a SQL injection attack, there's actually a couple of different things happening here, right? So a successful SQL injection attack, a packet is received by a web server, some sort of malcrafted input successfully bypasses the sanitation logic of the web application, and then it reaches the backend database where a SQL request has been reformed in the clear. So web server, web application, database. We actually need to understand the provenance of all these different entities in order to explain the attack succinctly. And so this is what the network provenance functions buy us. We can identify that a particular HTTPD worker was associated with a particular network input at a given moment. And then using the proxies, we're able to link that to the contents of the SQL request. So we can see here that, HTTPD worker read in a request from a particular remote host. And in the end, it accessed some information about our credit cards, right? So it would be relatively easy, thinking back to the DNC example, to make a rule such as, I don't know much about my system, but I know that PCI data should only be flowing to the Visa network. And therefore, if this goes to any IP address that's not associated with the Visa network, I know something's up, right? So we can use this to sort of perform data loss prevention within the system. Yet another example. Anyone remember what Image Tragic was? It was a pretty big deal. So Image Magic is this ludicrously pervasive image processing library that's basically the back end of everything that happens on Linux in terms of manipulating files or posting files. So it's common in a lot of different web services. And in spite of the fact that it's been around for decades, someone figured out that if you send it a malcrafted input that looks like this, I think this is a PNG file or something like that, you can basically perform arbitrary code execution. So I think this was a hot thing in like 2014. It's a little dated, but it's still relevant. And so again, the problem here is that we're dealing with some application-specific semantics like image magic. We're also dealing with the aftermath where someone's able to drop the shell, install a reverse shell on the machine, and do all these system commands. And so using this network provenance virtualization thing in tandem with operating system monitoring, we can reconstruct this very succinct explanation of what happened within this cross-layer attack. We see an HTTP request was used by one particular Apache worker. This is the normal operation of libmagic, image magic rather. And then when we upload rsh.jpg, all of a sudden we drop the shell and we do a bunch of nasty stuff. So again, we could make a pretty simple rule about how Apache is allowed to use the exec or the system call, right? And then if we see that it's using curl or it's using bash, I don't think it should be doing that, we can sort of procedurally stop these attacks in their tracks. All right, so how am I doing on time? 3 minutes? 5 minutes? All right. Wrapping up, hopefully I've shown you today that provenance collection is a good idea, right? It allows us transparency into the nature of these various system intrusions. And especially as we abandon the idea of perfect security and move into this world where, eventually a powerful attacker will get in no matter what, it becomes really important for us to understand what's happening in a system at any given moment. So hopefully I've shown you that not only is data provenance important, but also that we can perform various tricks to scope our data collection by leveraging foreknowledge about how the system is going to be used. And also that we can sort of compose data provenance that's being collected all of these different sources in order to solve higher level problems. What's next for me? I think there's all sorts of domains where this functionality is desperately needed. And so I'm looking into some more domain specific challenges there. Containers are a thing. They're very important. Oddly enough, the security community doesn't seem to be all that interested in them because they're basically overglorified cheroot, right? The isolation is not impressive, but the fact that people are using them regardless of what the security community thinks, that's a reason to take note. So we have these massive container clusters now that people are using to design these very same web services. How can we create provenance-based solutions to scale to meet the demands of security concerns in these kinds of data centers? What if the manager of my Docker swarm wants to have a succinct explanation in the form of data provenance of literally everything that's happening in the data center at once? Clearly, there's more work to be done here. There's also a few opportunities. Likewise, in the Internet of Things, we've got sort of unique problems. We've got this heterogeneous computing environment where, again, we've got all these proprietary closed source systems. I can't jump in and replace the kernel for my light bulb or something like that, right? Surely, a couple of dedicated grad students could do it in the lab, but what meaning is that going to have? Like, no one's going to use my provenance-aware light bulb, right? So the challenge then becomes how do we record this type of information in a system where everything's closed source, nothing's running on the same platform, and by the way, we might have 4 or 5 different radio interfaces in a single device. Wi-Fi, Bluetooth, Zigbee, Z-Wave, so on and so forth. There's all these different channels that could be used for attackers in such a system. And then moreover, since we're cyber physical, how do we incorporate notions of locality into all of this? I might have an attacker with physical access to my home that's driving through the neighborhood, or that's attacking over the internet through traditional means. So there's a lot of exciting things to tackle in this area of making transparent systems. With that, this work wouldn't be possible without my student Waji at the University of Illinois, some of my collaborators from Penn State and Lincoln, and my advisor Kevin Butler and colleagues at the University of Florida. Much of the code that I discussed today is available online at linuxprovenance.org. So, if you've got some course project coming up in the fall and you'd like to mess with this, feel free. With that, I'll take any questions. Thanks for your time. Yeah.
I'm always going to forget that. This provenance, this data provenance is stored locally on the Provenance like dispatcher, right? Either that's in the local computer, or in the case of the cloud environment, you have a separate machine, right? An attacker could if they're given access, if they're allowed to execute arbitrary commands, right? The attacker could erase this provenance information. Is that true?
So there's a couple things. Part of this has to do with the fact that I didn't want to spend an entire day talking about LPM, and so I apologize for that. I was like, it's secure, trust me. So yeah, we think about in a single host environment what we need in order to do that. The good news is, so first of all, we are assuming that mandatory access controls like SE Linux are enabled in order to ensure that nothing in user space except for the actual trusted computing base of LPM can interact with our components in user space, like our data store or this daemon that's receiving things from the kernel. It's such a simple workflow that it's very easy to protect, right? So it's like a 10-line SE Linux policy that says, nothing else in user space can mess with this. So since it's not network facing, we have a pretty reasonable, although not a verifiable guarantee that we should expect these things to operate unperturbed. In this case, where we're introducing these network facing middle boxes, things are a little dicier, and we don't fully have an account for that. The closest hand-wavy argument I could provide to you is that these things are, I think this one's on the order of a couple thousand lines of code, and this one's on the order of like 500 lines of code. So there's not too much room for, we could conceivably sort of formally verify these, although I have no intention of doing so, right? So we could take a look at this and make it. We could harden this pretty effectively.
The attacker could modify the stuff so to throw the forensics off the trail. They could it sounds like potentially if someone just wipes out your database that you're storing all this stuff in, that's pretty obvious. But someone could perhaps modify the existing provenance information so that it hides the fact that the stuff was modified or whatnot.
Yeah, that's a huge concern.
Right.
And so that's what we're trying to account for with these different security guarantees. So we have an answer for that in the single host environment. Effectively, the only way for you to manipulate the log is to actually perform an action. So it's not really a manipulation. There's not a way for them to claim they did something that they didn't because of the way that we're interposing on kernel operations. The only way that something winds up in the log is if it actually occurred. So if you inject a bunch of noise to make it confusing as to what your intent was, we need to account for that, but also we would still have an accurate description of what it was that you were doing. Similarly here, we're assuming that we've enforced some sort of some network flow rules such that the database can't be the middle box can't be bypassed in order to reach the database, right? So that we should have an accurate description of the events that happened.
Would cryptographic signatures of the provenance data would that help?
So that's something else that we've looked at. So in particular, if we're not relying on this core root of trust, which is the operating system, and there's arguments for you not wanting to do that, We might want, if we're in an environment where we have a network data center and we assume that anything's subject to Byzantine faults, some of my collaborators have shown that you can actually get some pretty good guarantees through using a message commitment protocol, which signs up on every packet. And as long as there was at least one remaining good node in the system that saw what the bad node did, then you can still figure out that something bad's going on in your network. So yeah, that's something else that that's happening in the field. Yeah. Cool. Any other questions? Great. Thanks for your time, everyone. It's a pleasure speaking with you.